Line A5, learning test number 7, we're going to take a look at power and power factor inside of balanced circuit systems. And I do want to note that it is inside of a balanced system. It's so important to understand that what we're learning inside of this one cannot be used in all installations. If you've got 3 different single-phase loads that you're connecting across from line to, multiple different across from line to neutral on A and B and C, and they're all different, you're not going to be able to utilize a lot of the stuff that we see inside of this learning task. So just bear that in mind. First of all, before we do any power factor calculations, we're just going to talk about power itself. You have learned this in second year. Power factor is equal to the cosine of theta, or the cosine of whatever angle we have for our circuit angle. So we've got cos theta, then we can go and figure out our power factor. We can just do that by punching it literally into your calculator with that angle itself. However, if we don't have that phase angle, we have to go and find the rest out through either trigonometry or through something similar to that. The other thing that we need to look at is going to be our formulas. Formulas that we often are going to go and use for power are going to go and be associated with our VA formulas. And our VA formulas are going to be the same for both Y and delta. And they are going to be that my E line multiplied times my I line multiplied by root 3 is going to go and give me the total VA, or the apparent power, of my circuit. If I then take my VA and I multiply VA times my power factor, I will go and get my watts that I would have for that circuit. Sometimes you'll see this written out as the VA formula, E line times I line times root 3 times power factor is equal to your watts. And they go through 2 different steps on, the Y-connected systems and delta-connected systems inside of your module over here, showing where the calculations come from, but ultimately they end up at these 2 formulas. And they say these 2 formulas are going to go and work for Y or for delta. Watts, E line times I line times root 3 times the power factor. VA is just going to be your E line times I line times root 3. After that, they give you a couple of problems for you to go and put together over here. So let's go and take a look at some of these problems, and we will go through what they are asking. Just erase this, and we will go straight to problem number 1. Problem number 1 says, what power is dissipated by a balanced, we want to see that in there, purely resistive Y-connected system if the line current is 20 amps and the line voltage is 208 volts. Well, that term purely resistive means that we are going to go and have 100% power factor. So we can just go and take our line voltage of 208, multiply it by our line current of 20, multiply it by root 3, and multiply that by our power factor of 1.00, 100% power factor, since it's a resistive load. When you punch all of this together inside of your calculator, 208 times 20 times root 3 times 1 is equal to 7,205.33. So we have a answer of basically 7.2 kilowatts that we would go and see for this. They give you another example, a current of 30 amps that is flowing through a circuit. We'll just go through that one as well. 30 amps that I've got from my I line. I've got 240 volt delta system. So E line is going to be 240 volts because it's delta. It doesn't matter. They don't say whether it's phase or line, but they're both the same inside of a delta system, multiplied by root 3. But this time they state that we've got a phase angle of 40 degrees. And so the problem is we don't really know what 40 degrees is. We cannot go and multiply this by 40, okay? That would be bad. We don't want to go and do that because 40 is in angular degrees. What we need to do is we need to go and find our power factor. And we can do that by taking the cosine of our angle over here. Our angle was given to us as being 40 degrees. So let's go into our calculator over here. We're just going to clear this. And we are going to go and do cosine of 40, which is equal to a 76.6 power factor. Perfect. So now that we know what our power factor is, 76.6%, we can go and substitute that into our top formula, times 0.766, like that. Okay, we'll go and put it through our calculator. 30 times 240 times root 3 times 0.766. 30 times 240 times root 3 times 0.766. And we end up with a total amount of watts of 9,552. So we end up with this value over here. You can check inside of your book. It should be 9.5 kilowatts that you end up for your total power. This is the total amount of kilowatts that we have over here. However, the question also asks for the apparent power. Remember that VA is apparent power and that true power is watts. So we found the kilowatts. We just need to go and find the actual VA. And to find the actual VA, we would go and punch this whole thing through without that 0.766. So we'll just try that one more time. Clear. We are going to go and do 240 times 30 times root 3, which is equal to 12,470.76. So 12.47 kilowatts would be our total VA, our 12.47 VA. 12.47 volt amperes of apparent power. And I have got 9.5 kilowatts. Last thing we're going to do is we're just going to do a very quick check to make sure that we're good to go. We did that power factor before where we took the cosine of the angle, figured out the 76.6. If our calculations are correct, we should be able to take 9.5 kilowatts divided out of 12.47, and we should end up at something very, very close to that. 9.5 divided by 12.47. Yes, we are doing a lot of rounding over here, but we just want to see if we're going to be close. 76%, that's the power factor that we were looking at before. It's just a fast mathematical check to make sure that, we haven't gone and screwed anything up too badly. There's another one in there. I'm not going to go through it. You can go through that one because that one's a little bit more tricky and it deals with a phase value of voltage, which means you're going to have to do some conversions to either go to the line values or do everything as phase values, voltage in the phase, current in the phase, and then multiply it by 3 instead of root 3. Either one of those is going to go and work. Let's talk about measurement methods. If we are dealing with a balanced three-phase system, we have got 3 different ways we can measure. We can measure with 3-watt meters, 2-watt meters, or 1-watt meter. The more watt meters we have, the easier it is going to be for us to go and measure out what exactly is going on. It's highly unlikely that you yourself are going to own a watt meter, much less 3-watt meters all at the same time, but occasionally companies have them. There are also a lot of really good power logging components out there that you would be able to go and run everything through. If you would have a large amount of current that you'd be trying to measure, you would also do that through the use of CTs, current transformers, to knock it down from the large amount of current down to something that would be usable for us. But we're going to take a look at our connections. The first thing I want to note about our connections is that they don't show the sections that are inside of here. That section inside there, actually that's going to be too small to read there. That section going across there is the ammeter section. This section is the voltmeter section. It's going to be the same for all of these. Ammeter section on the top and a voltmeter section on the bottom, because that's all that a wattmeter is a voltmeter and an ammeter inside of the same package that multiply their readings together. When we're doing the 3-watt meter method, what we're going to do is we're basically placing an ammeter in each line. It's the same as if we had an ammeter in each line. I'm just drawing them in separately over here. And that at the same time, we were also measuring values of voltage inside of each line over here. Sorry, I'm going to draw that as an actual circle here. But if you take a look at the connection that we have, you'll see that the connection is actually a delta type of connection. It's as if our voltmeter sections were all placed across the center and as if our ammeter sections were placed in line. This is those voltmeter sections. We see we're measuring the volts from the line over to a central star point. Across that one, we're going from the line to that central star on this one, and from the line over to that central star on this one here as well. So we are going to be measuring, if we take a look at it, phase values of voltage that we are running into these things at the same time as we are measuring line values of current, which seems counterintuitive. However, what we are doing is ultimately all power for this circuit has to go through these meters over here, which means that we're going to get a true capture of all the meters, and all we need to do to figure out what our total amount of power is we just have to go and add up whatever we have on this watt meter plus this watt meter plus this watt meter. Add all the watts together and you're going to get your total power. And you can use this watt meter method on either a delta system or you can use it on a Y type of a system. If you're using a delta like this one, then what you're going to have to do is you're going to have to create your own star point, which is what they've done over here with all the voltages. If we were measuring off of a Y type of system, what you would end up doing is you would connect this star point that you're making to the actual center neutral point of that circuit for more accurate measurement. Okay, 2-watt meter method, a little bit more similar, a little easier to go and work off of. We've only got two coils that are going to be working over here. We've got our ammeter one and a voltmeter, ammeter and a voltmeter. And the big difference between this and the other is that, yes, we've got an ammeter that's measuring all the current into the circuit, all the current going into the circuit. We then have all the current coming back out of the circuit. We're just going to draw it like this. I know it alternates, goes back and forth, but if we take a look at this, we can see that we would be able to measure all the current going back out of the circuit, and anytime that one of the other lines go high, the other lines are going to go and be measuring, the current flowing back out, etc. You will always capture all the current in the circuit using something like this. What this does, though, for its voltage connection is now going to be a line voltage connection. If you take a look, it is going across from this line over to this. So we are actually measuring a V line directly off of these ones over here. This one over here is going to go and have V line directly off of that one over there. Compare that with the first one. When we were looking at these, we were always measuring a phase value of voltage. Even on a delta system, we just created an artificial Y on the inside, and we were just measuring the phase voltage across that, whereas on the 2-watt meter, we're measuring directly line to line. The other thing that's fun about this one is that we can just go and add our 2-watt meters together, watt meter 1 and watt meter 2. Whatever I add them together is going to be my total amount of power, because once again, we're capturing all the current that's going through here. And I know you're saying, well, wait a minute, why did we have to add 3 before, and now I've only got to go and add 2? I'll tell you why. Because when we had the 3, we were dealing with individual phases. Now we are dealing with line-to-line values of voltage over here. So we're capturing the entire thing. And also, we're going to go and have surges. If you take a look at the way that a 3-phase system itself is actually operating, there's going to be times where all the power is being delivered along this line and it's coming back out on these 2 lines over here. So we're going to have a massive amount of power. We're going to have double the current that's going to be coming through there for a split second. And then it's going to go from the C phase being like that to our A phase having both currents going through and splitting. And then our B is going to have both currents going through and splitting, etc. And so it cycles through all 3 of those phases, and we are able to actually pick up and read the entire value, because there's always going to be one that any given instant is going to be higher. Now this is happening at a frequency of 60 hertz, so too fast for your human eye. It's basically going to push the needle over far enough that you are going to go and hold at whatever that maximum is, but that maximum that it's reading is going to be all of this over here. The other thing that's really neat about this watt meter method is that you're able to go and tell where your power factor is sort of lying inside of here, just off of the effect on the watt meter readings. If both of your watt meters are equal, turn to that chart on your page 72. If they're both equal, you're going to be at 100% power factor. If one watt meter is higher than the other, you're between 50 and 100%. These are the 2 things that you should always see. They should always be equal, or one should be slightly greater. If you're at one watt meter reading 0 and the other reading the total power, you're at a 50% power factor. This is a terrible thing. We don't want to see 50% power factors. And it can get worse if one of the watt meters is reading downscale You're going to have to go and reverse the voltage coil off of it to read back upscale. But if it was reading downscale, that means that you have now got negative watts almost that you're reading. It isn't negative watts, watts, or watts, but it's reading it as a negative value, which means that you're less than 50%. And you actually no longer can add them together at that point. At that point, what you would have to do is you would have to go and subtract the lower watt meters reading from the higher watt meters reading, from the one that are subtract the one that was reading downscale from the one that was reading upscale. The other thing that you can do with these 2 watt meters is you can go and read the total amount of phase angle that you have, or what your power factor is actually going to go and be. Take a look at that formula that they give you. Formula is cotangent, so 10 to the negative 1 of root 3, that's 1.732, times, stick another set of brackets around here, W1 minus W2. Look at all the brackets I'm throwing in here because I want to be able to go and calculate this one. Divide it by W1 plus W2. If you do punch this thing into your calculator, make sure you stick brackets, okay? When in doubt, just bracket it out. Stick enough brackets in there that you're always going to go and keep stuff grouped together. But you should be able to go and figure out from all of this your phase angle. And once you have your phase angle, then you can go and take the cosine of that phase angle, which is going to go and give you the actual circuit power factor from this. The very last thing that we're going to talk about is what's called the single watt meter method. That's where you only have a single watt meter. You're going to go and take an I line and E line reading. So it's as if this one over here just didn't exist. I'm going to go and insert it into the line here, take a reading. Then I'm going to go insert into a line here, take a reading. Then I'm going to insert into a line over here and take a reading as well. You can go and take the 3, add them together. They should all be the same if it's a balanced 3-phase load. Or alternatively, with that single watt meter, take the reading on one of the lines, multiply it by 3, and you're also going to go and get that full power off of it. All right, that's it for watts and power factor in balanced 3-phase. Once again, I want you to just be very, very careful with that. You cannot use these systems everywhere. You can only use them inside of those balanced systems. So don't try to apply this in any factory where you've got single phase and 3-phase loads and stuff like that going all over the place. This only works if you got a balanced 3-phase load, like a strictly just a motor or something of that sort. All right.